All right, so in chapter 13, we're going to deal with something called chemical equilibrium. Do you have any idea about what the term equilibrium means? It comes to the same, right? We've talked mostly about thermal equilibrium, right? When two things of different temperature reach the shared temperature, that's called equilibrium. And so now in chapter 13, we're really studying reaction equilibrium, okay? What happens in a chemical reaction? Up until this point, we've assumed that all chemical reactions go from reactants to products, and that's it, right? We assume that they go all the way to completion, which means we use up all of our reactants, right? We use up all of our reactants, including our limiting reactant, and then that's it, right? Our reaction's done. However, in reality, that's not always the case. So up until this point, we've just made this assumption that, yep, reactants turn into products, and then we're done. But that's not really what happens, right? What actually happens is that some of them stop short of using up all of their limiting reactants. Some of them continue to work back the other direction. They consider what's called a reverse reaction, okay? And so chemical equilibrium is the state in which the concentrations of reactants and products remain constant with time. So it's a point in which our reaction has reached the point at which it reaches equilibrium is when the concentration of our reactants and concentrations of our products are unchanging, right? They're done changing. Now, that doesn't mean that the reaction stops. It just means that the reaction is moving forward and backward at the same rate, right? Reactants are turning into products and products are turning back into reactants at a rate equal enough to keep our concentrations constant. Does that kind of make sense? So it doesn't mean the reaction stops, but it means that we're moving forward and backward at the same rate. Okay, so our concentrations essentially stay at whatever they were originally. Okay, so your book describes it this way. It says, on the molecular level, there is frantic activity, right? That's what your book calls it, frantic activity. And that means we still see molecules colliding and rearranging and bonding. But on the big picture level, right, it looks like nothing is happening because our concentrations aren't changing. But in all reality, they still are. Right? It's still moving forward and backward. Okay? All right. Here's a little diagram of what's happening with our rates of reactions. Right? Our forward rate starts out really quick. Okay, so think about this. If I have a reactant that starts moving forward really quickly, right? And then over time, my forward rate slows down. My reverse rate, which would be the rate at which my products turn into reactants, starts out at 0, right? At the very beginning of my reaction, there's only reactants. So I can't have any products turning into reactants at the very beginning. But as I form products, they can start forming back into reactants until they reach what's called the equilibrium rate, in which our forward rate equals the reverse rate. Okay, that's essentially what equilibrium is, right? Our forward rate equals our reverse rate, and our concentrations remain the same. Okay. All right, we said that equilibrium from the big picture, macroscopically, do you know what that means? Macro means bigger, right? So on the big picture, the reaction might look like it stopped even, right? It might have looked like we've hit a place of stop. But what actually is happening is that microscopically, we still have forward reactions and reverse reactions happening, but they are happening at the same rate. Okay, the way they described it in the book, as I was looking through it, was almost like a highway in and out of a city, right? As long as the traffic flow is consistently in and consistently out, right, it stays the same. The population inside and outside of the city stays the same. Right? But if I've got cars coming in and out at the same rate, that it looks like nothing is changing in my city, right? Does that kind of make sense on the big picture level? So it might look like not a lot is happening, but it actually is, okay? So at equilibrium, the reaction's happening on both forward and reverse directions at equal rates. At the beginning of the reaction, the forward reaction rates are higher. Can you explain why that might be? Why is the forward reaction rate, right? Forward would mean to the right. Why would the forward reaction rate be greater at the beginning? Say it again. Yeah, you've only got reactants to start, right? And so those will collide and cause that product to be formed. Once we get enough products, they will start combining again, and we'll go back to the reactants. But you can't form reactants if you don't have any products yet. So at the beginning of the reaction, generally, right, the reaction rate forward is much higher than the reaction rate in the reverse. Okay? Equilibrium can lay. We call equilibrium. Let me give you just like a sliding scale, right? This might mean it's all reactants present. This might mean it's all products present, okay? And let's just call this like a scale of 1 to 100 or something. Equilibrium could lay right here. It doesn't have to lay in the middle. This would mean that my equilibrium is to the right? If we're calling this middle or split evenly, this would be to the right. And that means that more of my products are being made, right? If I'm thinking about like the commercial scale here, if I'm in a production facility, I want my equilibrium to lay to the right. I want to produce as much product as I can, right? In other ways, it could lay to the left, which means we're not forming a lot of product. This equilibrium can change based on temperature, based on pressure. So there's all sorts of sets of conditions that can change where the equilibrium in a certain reaction might lie. Okay, so it's not just about the reaction itself. It can be about the conditions under which the reaction takes place. So in production facilities, right, where they're in charge of producing ammonia or whatever it might be, they have to have their reaction take place under a certain set of conditions to maximize the amount of product they can form, right? To make the most efficient reaction they can, they determine what sets of conditions will lead that equilibrium farthest to the right. Does that kind of make sense? Okay, so equilibrium doesn't have to lay in the middle. It can favor the products or favor the reactants. And we're going to look at how do we determine that. Okay, we'll get there. All right, this is a picture of what's happening here in this reaction, actually the formation of ammonia. This says the green is the reaction rate of H2. The concentration of H2, not the reaction rate. The concentration of H2 is the green line. The red line is concentration of NH3. And N2 is the concentration of is the blue line. So everything past the right of this dotted line here is at equilibrium. So does equilibrium favor the products or the reactants here? What do you think? What do we think? It's almost kind of tricky, but you see this up here has the highest concentration, and it is a reactant, right? Do we see what we're saying there? If this is concentration 0 through 10 molar, H2 has the highest concentration value because this line is up the highest. Are we good with that part? And so if this is a reactant, the next highest concentration is a product. The last highest concentration is reactant. I would still probably say that this one favors the reactants, right? Our highest concentration is in the reactants. Plus, that one has the highest mole ratio too, right? So we've really got more of that reactant in there. This question says, consider an equilibrium mixture in a closed vessel reacting according to this following equation. Okay, so we've got water plus carbon monoxide yields hydrogen gas and carbon dioxide. You add more water vapor or H2O gas to the flask. How does the concentration of each chemical compare to its original concentration after equilibrium is reestablished? Okay, so let's say we're at equilibrium. We've reached an equilibrium point, and now we put in more H2O. I want you to just sit and kind of chew on that for a little bit. What will happen to the molarity of each of these compounds after we reestablish equilibrium, right? We add something into it and equilibrium has to be reestablished. So I want you to chew on, do you think this molarity will go up or go down? Molarity will go up or go down, up or down. Okay, so I want to give you like a minute to chew on this and see what you think, and then we'll kind of come back to it together.
Because if you have more H2O, that means after you'll have more H2.
Perfect, I would agree. And so that means also CO2's concentration will also increase. Good. Does that make sense? We just added more reactant, so naturally we're going to have more product, right? I would agree with that. What happens with CO? No, it can't stay the same because it's either going to react with water or it's going to have more of it coming back. So what do we think? Not quite. What I think is going to happen here is that my concentration of CO is going to go down. Because when I add H2O, it's going to collide with whatever CO molecules are left and form a product, right? It's going to use up whatever carbon monoxide molecules are left in there, right? By me adding in more H2O, it's going to find whatever CO molecules are left and form those products. And we will still, start in the reverse, but it's not going to be enough to make up that rate. So I think the concentration of CO will decrease. Okay, what about the concentration of water? What will happen to it? It's going to go up. Yeah, I think it's going to go up, right? Because we added it to there. Like we literally just added more of it in there. So we've got to have more of that gas in the container. It's going to be higher than water concentration will be higher than the original equilibrium concentration, but lower than the initial total amount. Yeah, because it's been used up. Okay? All right, we're going to think about this same type of question here. I think I've got the answers on the next slide, but we kind of talked with that. Same type of question here. I'm adding more H2 to the flask, not H2O. How does each concentration compare? So let's see if we can work through this one. Now I'm adding more H2 to the flask. Will concentration go up or down, up or down, up or down? If we feel like now it's just the opposite, I would agree. These concentrations will both go up. We'll be able to form more products. I think CO2 will go down. And H2 will be lower than its initial concentration, but higher than its previous equilibrium concentration. So this would increase just a little bit. Okay, do we see how the addition of these things can shift equilibrium? Right, that's essentially what Le Chatelier's principle is. And we're going to, again, dive into that later in the chapter. But we're going to look at how do reactions change based on the addition of things or shifts in conditions. Yeah. It's going to have higher concentration than its previous equilibrium because we added it to it. It won't have as much as it did to start the whole reaction because we've used up some of it. But its previous equilibrium, whatever it was, we added more to that. So it's going to be a little bit higher. Okay. All right. So that's just, again, walking through that. All right. We're going to get now into what I really think is the meat and potatoes of this chapter. We're going to start the math part, what's called the equilibrium constant. I think it might be helpful for you guys to make yourself kind of an equation sheet for this chapter because there's going to be lots of little tidbits that we're going to get throughout. I am going to give you kind of a one pager like I did with equilibrium, with kinetics. I gave you that one page about differential rate law, all that stuff. I'm going to end up giving you that, but I want you to build one on your own first, and then we're going to compare and see if there's anything different. But this is something called the equilibrium constant. And this basic equation, this template equation is what I do think you should have on this equation sheet. Okay, this is the template for all equilibrium constant questions. Okay, it takes your reaction, coefficients, and formulas, and it puts them equal to capital K. All right, capital K is the equilibrium constant. Sometimes you'll see it listed KC. I never put that, and your book doesn't put that, but I just want you to see that if you should happen to notice it. KC is your equilibrium constant. Yeah, very good. These are both, they're in different fonts, but whatever the coefficient is needs to become your exponent in the equilibrium constant equation. Okay, so whatever your coefficient is has to become your exponent. All right, do you remember what these square brackets mean? They mean the concentration of that thing. So typically they're measured in molarity. And we know that molarity is moles per liter. We feel really comfortable about using molarity. Molarity is moles per liter. Okay, because sometimes in our questions, it will ask you to calculate that really without even thinking about it. So that just has to be something that you do regularly. Okay, so that's going to be concentration. So A, B, C, and D are whatever our chemicals are in our problem. Square brackets mean concentrations. L, J, K, L, and M are the coefficients, and K is called our equilibrium constant. For some reason, okay, and your book goes into more detail about it, but I don't care. K is given without units. So there is no unit for the equilibrium constant. Okay, there's no unit for equilibrium constant. And the last thing I want to mention, actually there's two things here. K only is true at a certain temperature. Okay, so there might be different equilibrium constants if your reaction changes temperatures. But in the problems, it will just tell you, at this temperature, K equals whatever. If you're doing real lab studies about K, you would have to be really particular about temperatures because it can change your equilibrium constant. Okay? All right, last thing here, I want you to circle that. Highlight it, whatever you need to do, but only gases go into this equilibrium expression. Okay? Even if we're talking about pressure, we're gonna be able to use this equation looking at pressures in flasks too, but only gases go into our equilibrium expression. So you have to be actually paying attention to the states of matter in the reaction now, right? We've always been able to kind of ignore those, but we actually have to pay attention to them now. We just leave it out, or in aqueous, we leave it out. Yep, only gases. So you'll see most of our reactions are all gases, but if there's a solid, we just really get to ignore it because it doesn't change the pressure of our flask or the concentration of our gases there. Okay, all right, write the equilibrium expression for the following chemical reaction. So all we're going to do is write it. We don't even have to calculate it because they didn't give us concentrations, but we need to be able to write the equilibrium expression. So we know that K, did you guys pay attention? Which goes on the numerator of this? The products. That's really just something that it seems counterintuitive, right? If we were going to go just write it out, we would put reactants over products, but we need to pay attention. It's going to be products over reactants. So I'm going to go concentration of NO2 to the what power? Fourth power. And then concentration of H2O to the sixth power. And then in the denominator, I would go NH3 or ammonia to the fourth power times O2 to the seventh power. So we do need to make sure that we understand these two terms would be multiplied by one another, right? Multiplied by one another, all that kind of stuff. Okay. I will tell you, for most of our problems, you won't see coefficients of 4, 5, 6, 7, right? It's mostly 2s. The way these ones work out are for the problems that we do. Most of the time, you won't see these big exponents. And I wish I had a value range for you for K, but I've seen all the way to -6, and I've seen all the way 10 to the -6 and 10 to the +6. I can't really give you a range as to what our K value should equal because it's just dependent on concentrations and coefficients there. So a little trickier. Okay. All right, let's try this one. Calculate K for the following reaction. Concentrations are given at equilibrium. So let me explain why I put that, okay? If we want to calculate K, if we're dealing with K equals something times something over whatever, right? If we're dealing with our equilibrium expression, we assume that this is at equilibrium, okay? We don't calculate K at the beginning of a reaction. We calculate K at equilibrium. So that's just important, okay? Okay, balance the reaction first. Okay. 2 ends. I need a 2 there. That gives me 6. And so my H has to get a 3. Okay, so we need to balance that there, so we have that. Is there supposed to be 2 NH?
Not in the balancing, in the concentration.
Ew, no. No, let me look at what it should be. Yeah, you're right. One of these, I'm going to assume that this is the first one's supposed to be N2, but let me look at the book problem I put in so I get it right. All right, I have to make a quick edit here. I think I wrote these down in the wrong order. Okay, so concentration of H2 should be 0.0 0.031 molar. Concentration of N2 should be 0.85 molar. Okay, sorry about that. I need to fix that on my slide. All right, so now when we go to put it into our equilibrium expression, we would say K, we're solving for K, equals products, so 0.031, and to the what power? Second or squared, right? And then on my denominator, I'll take the concentration of N2 times the concentration of H2, and that would be Q. Okay. I got something pretty large. I got, oh, that's what I got. Okay, and so they rounded this to 3.8 times 10 to the fourth, just because of significant figures. But I don't know. I'm okay with everything being. I mean, I'm good with either. I'm fine with either. I just don't like using scientific notation. That's just my preference. But
I got 37.9506.
okay, so that means you're 3 orders of magnitude different from what we are. This says calculate the value of the equilibrium constant for the following reaction. This is something called K prime, and it's the equilibrium constant of the reverse reaction. So if it were asking for the equilibrium constant of the reverse reaction, that would change my expression by doing the inverse of that, right? You can just, so the no. If it's written like this, right, which they already flipped the reaction, we're still going to go products over reactants. But if it was written just normal like it was in the last one, we would flip it. Yeah. Yeah, use the same concentrations, you would just flip them.
Did you just get what you got last time? Just put that.
Yes, that's a great question. What this boils down to, if we already know K, then we can say that K prime is equal to the inverse of K, right? 1 over K. So that makes our time a lot quicker. If we're just inversing our fraction, we might as well just inverse the number that we already know. So we could have plugged it in and solved for K prime using our other concentrations, but instead we can just take 1 over 37, I don't know what it was, 950, and we get K prime equal to 2.6 times 10 to the negative fifth. Right, so if it ever asks you for the equilibrium constant of the reverse reaction, that means we're just going to flip it, right? We're going to do it backwards, okay? Or if you already know K, you can do the inverse of that K. You can use the same concentrations, but they cut the reaction in half, okay? They cut the reaction in half. So let's see how that changes our K value, all right? I'm going to solve for K. And I'm look back at my other concentrations, right? The original ones they gave us. So NH3 was 0.031. This was 0.85. And this was 0.0031, right? Those were our original concentrations. No, I'm backwards. My goodness, I can't get these together. Okay, N2 is 0.85. And this is 0.0031, sorry. Okay, so if they ask us for the equilibrium constant of this reaction, my numerator is just 0.031. My denominator is 0.85 to the 1/2 power and 0.0031 to the 3/2 power. Did you guys get about 194.8? And so you see what happened to our reaction here? We cut our whole reaction in half from our original. And so what we did essentially was take K to the 1/2 power. Okay? So if I took 37,950 to the 1/2 power, right? 37,950 to the 1/2 power, then I get the same thing. 194.8. So I can manipulate that. I can manipulate K however my reaction was manipulated. Right? If I took my reaction times 3, I would then cube my K value and I'd get my new reaction constant. The equilibrium expression for a reaction is the reciprocal for the reaction written in reverse. So we said K prime is equal to 1 over K, right? If we want the reaction constant the equilibrium constant for the reverse reaction, we just take the inverse of that. When the balanced equation for a reaction is multiplied by a factor of n, in our case 1/2, the equilibrium expression for the new reaction is the original expression raised to the nth power. So our K double prime, that's just the next version of K that we solved for, was equal to K to the n power. All right, so those are we looked at both of these examples. We found K of the reverse reaction, and we found K of half that value. So however we manipulate our reaction, that's how we manipulate K also. Okay? And we already said K is often written without units. So that's just another thing to remember, okay? This example comes from our book, and it says K always has the same value at a given temperature, regardless of the concentrations of our reactants or products. And so this gave 3 different experiments, and it gave different reaction concentrations for all 3 of our species in the reaction, different concentrations for every one. And when we run out the calculations, we get the same K value. So K is dependent upon reaction, obviously, but also dependent upon temperature, not dependent upon concentration. So we can look at it in lots of different trials, but our K value for a concentration at a certain temperature will remain constant. Okay? All right. For a reaction at any given temperature, there might be equilibrium positions, but only one equilibrium constant. And so what we mean when we say an equilibrium position is actually a set of our concentrations. And so if I look back here, this would be considered an equilibrium position, right? That set of concentrations. This would be considered an equilibrium position, and this would be considered an equilibrium position. It's just a set of our conditions, but we only have one K value for all of those, right? K is the same throughout all the trials. Yeah,